In this unit, we're expanding the ideas that we understand about how functions can operate. And we've been looking at functions that are recursive, meaning they can be defined in terms of themselves. And today we're going to look at higher order functions, which is going to allow us to treat functions as values and functions as parameters. For that to make sense, let's build up to it first. But before we get into it, some announcements. I want to remind everyone that tutoring is still going on digitally over Zoom. We have some awesome UTAs who staff tutoring on Tuesday through Thursday, 5 to 7 p.m. This is a great opportunity to come and discuss something that didn't make sense in lecture. If you have questions about something that came up in these videos, this is a great way to talk through it with some senior UTAs. Next Thursday, we're going to be hosting a diversity in computer science panel discussion. And we'll have representation from broad strokes of the computer science community, including current students, including recently graduated students, and folks who have been in industry for a little bit longer. This is an event that we host every semester, and it's always exciting. This will be the first time we've done it digitally and remotely, but we'd love for you to join us. Go ahead and pencil it in if this sounds interesting to you. If you have questions about what the path forward looks like in computer science, April 16th, 6 to 7 p.m., everyone is welcome. There is currently a worksheet and a problem set out. I would be focused on getting those turned in, the worksheet this week and the problem set by beginning of next week. These are practice with recursion primarily. All right, so just to sort of frame the discussion and where we're going with today's new ideas, I want to start from a place that should feel familiar and relates back to an algorithm that we looked at last time. So if you'll take a look at these two function definitions and then on Gradescope, respond with how you believe these two functions differ, pause the video here and resume when you're ready to move forward. All right, so what you can tell is that there's a lot of similarities here. There's a lot of redundancy. We see that the overall structure of the if statement, if we have our base case here, right? We're talking about a recursive function. This would be our base case. When we reach the end of it, the same base case is in both places. We see that when we are testing for something, the test is changing, right? This part is changing, but what we're doing, depending on if that's true or false, is effectively the same, ignoring the fact that these functions have two different names, right? So the underlying algorithm or the process that we're applying in each of these functions is the same, right? We're trying to filter some input list of numbers down to some numbers that meet specific criteria. And all that's really changing between these two functions is what is that criteria? And because we need two different functions in order to filter in these two different ways, we would have to name them differently as well, right? But one of the things that hopefully at this point in the semester you're starting to get a feel for is that when you have a lot of redundancy in two pieces of code, right? When you have a lot of things that are duplicated, and in this case we see a lot that feels very similar here. It feels like just some minor details of these two things are changing. There's usually an opportunity to rewrite something where there is a lot of redundancy to make it possible to have only one function that could do both of these things and that would allow us to plug in what it is that makes them unique relative to one another. Right? So this next question is, given this filter function that's defined on the left, which is very similar to the ones we just looked at, it's different in its Boolean test condition here. This question is about, hey, given the way this function call to the test function is used, where it's used and what its argument would be given this example code, which of these function definitions is correct for this test function? If we were to have defined a function named test outside of filter, which of these function definitions would have been correct for us to be able to make use of it in this position in our program? So once again, pause the video here, think through this, and then respond on Gradescope with what you think it is, and resume the video once you've done that. Okay, we know that for a function call to be valid, two things need to be true. right? We need to give it the right arguments that correspond to the right parameter, right? So the parameter type that is defined in the function must agree with the argument type of the function call. So we need to figure out what is the type of first L here. And then the return type, right? So the return type of each of these definitions, that's going to need to make sense given the context of where this function call occurs. Right? So let's focus first on breaking this problem down. And the first question is, what is the type of first L? Right? Well, if L is a list of numbers, we know that the first function will return the first value of that list, which would just be a number. Right? So we know that this test function is going to need a number parameter. Right? So I'm going to change colors here and go through which of these test functions has a number parameter. So it looks like the A definition does, the B does not, right? So that doesn't work out. The C does, and the D implementation does not, right? So we can narrow down what might be valid here by looking at, okay, when we call this function test in this example code, first of L is always going to be a number, so it's got to be either A or C in terms of this definition. Now the next question is, what does the return type need to be? So notice we are using this as the condition of a Boolean test, right? So if this value returns true, then we are going to do this then block, right? Otherwise, we would jump to the else block. So given that extra bit of information, if a value we expect to be either true or false must be what we need in this position, then this test function better return a Boolean. So we can look, and A does not return a Boolean. B does, but we've already ruled it out because of the string parameter. C does return a Boolean. So it looks like C would have been what we expected to be the correct definition of test, right? And what I want to emphasize here is notice that we don't actually care what this test function implements. The logic of this test function could be anything we wanted it to be, as long as we took in a number as a parameter and returned a Boolean. Test could be any logic we wanted that returned a Boolean value, right? And so it looks like we are making our way in a direction that might allow us to, redefine what test is in order to plug in different logic at this step. And that is, in fact, the direction we're moving in. So going back to that first question just briefly, if we think now with both of these questions in mind, in this example, filter positives and filter negatives, the same overarching logic is applying here. We're trying to filter a list of number nodes down to only those that match some criteria. In this case, it would be the values that are greater than 0. So we would get a list back of only the positive numbers. And in this filter negatives, we would get a list back of only the negative numbers. Notice that the only really substantive part that's changed is the logic here, right? The algorithm otherwise is exactly the same. The logic is otherwise exactly the same. But this test condition is all that's changing. And it would be pretty great if we could just plug in different test conditions to one function, perhaps named just filter, right? So maybe we have one function named filter, and we could somehow substitute out and provide different logic when we called the function rather than having it hard-coded inside of the function. So what we would really like to be able to do is pass a piece of logic into this function in some way. And we're going to be able to do that by separating out the algorithmic logic of filter in this algorithm, which is an extension of the bouncer algorithm, right? So bouncer was a preview of this more generically defined filter algorithm, and then the test that we're actually applying in that given filter. Right? So if we think about the definition of filter that we looked at in the second question, right? Filter here is given any list, and then we're using some function named test to decide this logic, right? So maybe that test function implements if this number is greater than 21 or equal to greater than or equal to 21, return true, otherwise return false. Maybe it's testing if the number that it's given as a parameter is positive and it returns true or false otherwise. Maybe it's if it's negative. The key idea here is we could give, as long as this test function can take a number and return a Boolean, we could plug any test function we wanted in there, right? But we don't, as so far as we know, have a means for substituting in different test functions at this point. So for example, as I just mentioned, either of these two functions is positive or is negative. If they were named test, right, they would have worked in this position because both take a number and return a Boolean. And what we'd really like to be able to do is plug in and say, hey, filter, use the is positive function for your test function. Or, hey, filter, use the is negative function for your test function, and filter based on that criteria. So what if we could make test a parameter of the filter function? What would that mean, right? What would it mean for us to be able to pass a function into another function, right? So that we could say, hey, filter, here's the list I want you to filter, and here's the function I want you to use to determine whether or not a item passes the filter or is rejected by the filter, right? And is included in the output list or is not included in the output list. So we do know that both of these values, or both of these functions, would satisfy the requirements that are needed to be test if they were just named test, right? So wouldn't it be nice if we could write filter in such a way that we could say, hey, filter function, filter on input, which might be this list of numbers here, -1, 2, -3, 0, 4. And my second argument here is the function is positive. We're trying to assign is positive to the test parameter in this function call, right? So we call filter, we give you the list of inputs, and then what we'd love to be able to do here is say, hey, use this is positive function as your test function, right? So this would allow us to substitute in any logic we wanted at this position, right? Similarly, we could use that exact same filter function to pass the function is negative to be the test function. And this would give us a way of substituting or plugging in the logic of these two functions for this test parameter, right? But we have this problem, like what would the type of this parameter be? This is a function. We don't know what a function's type is yet. So we have a mystery to resolve here. What is this test parameter's type? We're going to explore that in the next video.